I hope you got a sense by now that all these feedbacks, positive and negative feedbacks, and the ENSO life cycle with the recharge or the discharge onset, the evolution, growth, mature phase, and decay phase give you a sense that maybe there is some predictability in the system. Turns out to be mostly true. So now ENSO prediction is a big business. I just picked something from the International Research Institute for Climate Prediction, but now the name has changed into something else. This is at Columbia University, and CPC is the Climate Prediction Center of NOAA. Together they put out this kind of forecast. This is for early February 2021, so basically the latest one. And this is kind of a probabilistic forecast where they show the probability of the coming seasons. So this is February, March, April, May, and so on going into 2021 of the year that is currently in a La Nina already since last year, of that La Nina disappearing and maybe reaching or surviving through the summer into the fall of 2021, or the forecast of neutral forecast. So that's coming to be 60% and then dies off, and then La Nina goes up and so on. But basically you can see that El Nino has a very little probability of showing up this year in 2021. Okay, so the other way to look at it is this way, where multiple models are taken here. These are the various models that are dynamic and statistical, and they all issue their forecasts starting in January, going out into the rest of the year in 2021, and the dynamical and statistical averages are also shown here, and essentially they forecast the mean of these models essentially is for a near neutral year. Although some years are way out here predicting a strong El Nino, some are out here predicting a strong La Nina to continue from last year into this year. So does it matter when the forecasts are initialized? This is one of the questions, and this book spends some time on talking about this persistence of the annual cycle and a so-called springtime persistence barrier. When we looked at the annual cycle, we saw that during springtime the east-west SST gradient flattens almost completely. The eastern Pacific gets warm as the sun is crossing into the northern hemisphere in the equinoctial season, and that leads to what is called a springtime barrier. So this is showing annual cycle of the mean sea level pressure at Darwin and Tahiti. So you can see the Tahiti and the differences in the monthly mean pressure. There are ±1 standard deviations shown here, and the differences between Darwin and Tahiti reach towards their minimum in the spring months before they pick back up. Okay, so the system itself is got a, let's say, a low signal to noise ratio in some sense of the annual cycle, but this also shows up in other things like lagged correlations of the Southern Oscillation Index, so Tahiti minus Darwin. So here annual cycle of persistence is shown, lagged correlations of monthly Southern Oscillation. So this is the correlation, and these are the initial months, and these are staggered so that July corresponds to July and so on. So you can see the staggering there. The letters indicate the anchor or starting month of the correlation. So how July correlates with the other months going into the future, how May correlates, and so on. The lagged correlations also decrease abruptly in the boreal spring. Okay, here these you can see that there is a sudden drop in correlation, and then there is a flatter change and the drop doesn't continue. Okay, so SST persistence between JJA and DJF, DJF and JJA, all these kinds can be looked at, but the main point is that when this annual warming, spring warming happens and the east-west SST gradient relaxes, the system is very vulnerable to perturbations. So if you start a forecast before, then surviving through this annual cycle persistence barrier is a problem. So this is also then becoming what is called a spring predictability barrier, which can be seen in many ways. So this is the 6-month persistence of SST anomalies going from June, July, August to DJF. So there is a high persistence in the El Nino region here. Northern Indian Ocean shows some persistence, and there are other regions which show persistence, but we will just focus here, let's say, on the tropics. And if you look at DJF to JJA, then the equatorial region basically has no persistence, whereas the Indian Ocean has increased persistence from JJA to from DJF to JJA compared to JJA to DJF. Okay, so there are region-specific physics which provide these changes of persistence of the annual cycle from one season to another, and you can look at that in terms of the starting season and along the longitudes. So the Atlantic has various persistences. So DJF into JJA is reasonable, but JJA into DJF kind of has a minimum, and then again DJF to JJA. So that's just repeating the annual cycle. Here is the Indian Ocean, and here is the Pacific. So this spring predictability barrier or spring annual cycle persistence barrier clearly shows up here in terms of the lack of persistence through some seasons. When you do dynamical forecasts, there are various ways in which these are considered, so it's not discussed as much as it has been in this book, but one can look at real-time forecasts of ENSO variability and look at the decadal time scales of changes in persistence with respect to lead time. So lead time means basically if you're initializing, let's say, on February 1st and predicting out to 6 months, then it's the February initial condition predicting into the fall months, and then March into whatever. So the predictions are typically done maybe every week or every month, depending on the computational resources, and ensembles are done, either multi-model ensembles where multiple models are taken, or each model has a perturbation of the initial conditions to make multiple forecasts of 6 months, 9 months, 12 months, and so on. Each model does their own thing based on their own skill assessment. This is basically showing that the spring persistence barrier is clear. If you start in March, the persistence drops clearly after as you get into the spring season, and that persistence has a decadal variability. That's all the point I will make, because I don't want to dwell too much on this specific thing that the book considers in great detail for the author's personal interest. So December persistence, March persistence, June persistence, and September persistence, they're all slightly different, and there is a decadal variability in the persistence. So the background state itself changes the way El Nino teleconnections work and so on. So this is a statistical model, and this is a simple dynamic model, and you can see that they all have this, they are prediction models, so they are showing correlation coefficients, and generally if the correlation between the model forecast and the observations are above 0.6, you are doing really well. So these are very high correlations here, but they quickly drop when you are trying to get through the spring months. So you can see that here here as well, and this one is doing various initializations and then forecasting out to literally more than a year, but you can see the persistence barrier of the spring months that is related to this signal to noise ratio in the Pacific in terms of the basic state changes. This is another way to look at it: annual cycle of predictability in the equatorial Pacific in the European Center for Medium Range Weather Forecasts, so ECMWF. This is one of the most skillful models and relied on by many countries, and other countries are competing with ECMWF to beat it. This is a coupled ocean, atmosphere, land operational seasonal climate model. So it's showing Nino 3 SST and Nino 4 SST. And again, these are the lead months and these are the initial months. So if you start in November and look at lead times, then you can see that the persistence of the skill, the correlation shown here is pretty good. So high correlations means forecasted model forecasts correlate well with observations. So these are done for previous years. But if you start here in the, so coming down, January is okay, February is still okay, but if you start here, you can see that suddenly the spring persistence barrier hits you, spring predictability barrier hits you, and that is a problem for forecasts. Okay, so just remember it. It's still not completely understood and not solved. There are various attempts of data assimilation, proper initialization in terms of not just initializing the ocean, which has the memory, but also the atmosphere as a coupled system, and to see if spring predictability barrier can be overcome, but still not done as of yet as far as I know. Okay, so just remember that as one of the quirks of ENSO prediction business, which has a lot of value because it has implications for health, agriculture, water resource management, energy management, civil conflicts, all sorts of things. So ENSO prediction is really important, and every country wants to improve skills. For a country like India, which wants to do monsoon forecast, doing ENSO forecast properly is very important because a lot of the predictability from monsoon may come from ENSO itself. Okay, something to remember.